I hold in my hand a nice little component. It's very small. That is in your kit. It's got some squiggly lines on top. It's got long legs coming out of the bottom. It is a photoresistor. We're going to learn how to read the amount of light striking the photoresistor. Then your Arduino can respond to ambient light conditions or a signal shining at it or something like that. Now, this thing, it's called a photoresistor. Maybe you could guess. It's a device that has a special chemical property, or a sort of semiconductor chemical property, we could say, that changes its resistance, i.e. the resistance between this leg and this leg. It's a resistor whose resistance varies based on the amount of light hitting it. And it adjusts pretty quickly. So when a different amount of light hits it, the resistance changes pretty fast. We're going to build a different kind of circuit than we've seen before to read that changing resistance. And so I'll start by showing you the schematic drawing for this. And though there are some different ones, just pay attention to those tiny little squiggles, because the schematic drawing I prefer reproduces that. It is a case where the thing kind of looks like its schematic drawing physically. I draw a kind of series of squiggles like this and put a kind of oval shape thing around it. Wire coming out of the top and the bottom, and that is our photoresistor. Now imagine you just plug the top part of the photoresistor into 5 volts. I'll put my Arduino over here. That's also plugged into 5 volts, and ground is plugged into ground. Imagine, if you will, well, first of all, I want you to consider what is the kind of signal we're going to be getting off of this. Is it going to be either 0 or 5 volts, or will it be something in the middle range? Well, it's going to measure the amount of light hitting it, so it's not a yes or no. There is or is not light hitting it. It's a kind of a varying thing. It's a continuous thing. So we're going to use an analog input pin. Let's say a 3. Imagine if we wire it up like that. So let's say this is very high value resistance. Let's say it's a 10K resistor right now because of the amount of light hitting it. Well, how much voltage will pin A3 see? In that moment, 5 volts will be connected through a 10K resistor to pin A3. A3 will see 5 volts. What if the amount of light hitting this changes it into a 100 ohm resistor? So the resistance drops drastically. Then at that moment, pin A3 will be connected through a 100 ohm resistor to 5 volts. Pin A3 will see 5 volts. So this circuit, as drawn, is actually not sufficient to measure a changing resistance, because it doesn't really matter what the resistance is. The only voltage attached to pin A3 is it's always going to just be 5 volts. And it just doesn't matter. This will not tell us anything about that changing resistance. We have to build a slightly different kind of circuit. We have to add something on in order to be able to measure that. What I'm going to do is draw a dot here. That dot is a node. It's a place where multiple wires meet. And I'm going to add a different resistor coming off of that node. And at the far side of that resistor, I'll apply ground. Now, let's imagine in this moment, let's say this is a 10K resistor right now, and this is also a 10K resistor right now. So if you're pin A3, you're in the middle of 2 different 10K resistors. Over here is 5 volts, and over there is ground. You are directly in the middle. It is kind of like that moment in a potentiometer when your arrow is pointing right at the middle. It's kind of like that moment in this circumstance. 10K here, 10K there. Pin A3 will be exactly in the middle, and it will see 2.5 volts. Fine. So it'll say, if it's reading 2.5 volts, think about what that means in terms of analog read. 2.5 volts is halfway between 0 is the minimum analog read, 1023 is the maximum analog read. So what do you think the analog read would be? Think about it for a moment. If you answered about 512 or so, then you're right. But now, let's say the resistance here changes because the amount of light hitting this changes. Let's say instead of 10K, it becomes 2K, 2,000 ohms instead of 10,000 ohms. Now the total amount of resistance between 5 volts and ground has changed. It used to be 20,000 ohms, now it's 12,000 ohms, but that's not really our concern. Our concern is, what is pin A3 going to see? Well, look back at the potentiometer equivalent. Now the arrow has moved somewhat because there's only a little bit of resistance between 5 volts and this point, and more resistance between this point and ground. So it's kind of like the arrow is farther to the left at this moment. In fact, the arrow is 2/12 of the way over. So the math says if we multiply 5 volts times 2/12, that's 2 out of the total, which is 5 times 1/6, which is 5/6 of a volt. In fact, if we have a 2K up here and a 10K down there, we would expect pin A3 to read 5/6 of a volt, which is 0.883 or 86, I don't remember. I think 0.83 volts. And 0.83 volts, we would have to turn that into an analog read value, and then we'd get the analog read. It would be something like 100 or something like that. So the moral of the story is we have to build this certain kind of circuit, which is called a voltage divider. And in our case, we're not going to use a 10K resistor down here. Instead, we're going to use a resistor that you do have in your kit, which is a 5.1 kilo ohm resistor, and I'll make clear that that's a 1. A 5.1K resistor would be the short way of saying that. If I take these hard to read colors, but I will tell you what the colors say, and you'll just have to take my word for it. So the first color is green, then brown, then black, then brown. The color green encodes the number 5. Brown encodes the number 1, so far we have the number 51. The next color is black, which is the number 0. So we have the number 510, which is 510. And that last band over there is brown. So 510 times 10 ohms equals 5,100 ohms. So that's one way to read what this resistor is. Another way is to use a multimeter and actually just test the resistance from here to here. And if it's about 5,100 ohms, it's the right value resistor. Another way is, when you get your package out, the groups of resistors are labeled, and this will be called something like 5.1K. Sometimes it'll be called 5K1. 5K1 is electrical engineering speak for 5.1K. In any event, that's the resistor of interest. So now let's build that circuit. And be sure you're selecting the right resistor. If you don't do that, it isn't going to really work right. So this can be a little confusing, even though it's a really simple circuit with only a few wires. I'll put this over here. Actually, it's easy to mess up and get this wrong. So let's just take it step by step. The first thing I'm going to do is take my photoresistor and connect one side of it to 5 volts and the other side to some node. That node being some place in the breadboard that we're going to connect other stuff to. I actually don't need this extra red wire. If I want to connect one side of this to 5 volts, I'm going to make my 5 volts go over to this side. I like having power on the right and ground on the left. If I want to connect one side of this to 5 volts, I can just plug one side in straight to 5 volts. Try not to bend the little legs like I just did. Now the other side plugs into some point in the board. So let's, I don't know, how about that place? Fine. Okay. Now that is a place that's going to need to connect through my 5.1K resistor to ground. So I can take my resistor, plug one leg into that same place, that row, and plug the other leg of the resistor right into ground. So far, we have built this part of the circuit and this part of the circuit. We are missing only a single connection, a single wire. And for that single wire, I'll plug into the same row, the same node in the board, and I'll connect it to the pin of interest. In this case, it's pin A3. And make sure I'm looking from the edge to ensure that, yes, I am plugged into A3. I know that it's upside down, but at least you can see it's the right value. So that's the totality of the wiring. I did the wiring while it was unplugged, always a good idea. And now we are going to be able to read that resistor value and it should vary when the amount of light striking it changes. Let's go over into the software, which should be pretty straightforward, but we'll still write the software. Read a photoresistor. How much light is the question we're going to be answering. Read on pin A3. I'm going to start with a const int photo pin equals A3 because then we can just refer to it by that pin number in the future, by that pin name in the future. Next, I'll enter my setup, and I should declare that pin as an input. And because I'm going to want to get feedback back to me, the user, I'm going to turn on the serial communication. Serial.begin 9600 is the standard rate. Nothing surprising so far. Void loop. Well, what do I need? I'm going to do an analog read of that pin, of photo pin. Should I store it into a value? I sure could. I could say int photo val equals analog read photo pin. Now photo val will contain that number. I'm going to print it back to the user, serial.println photo val. If I were to do serial.print without the ln, extra parenthesis. If I were to do serial.print without this, it would just be a single line of numbers, very hard to read. So the print.ln is useful. And finally, let's give ourselves a little bit of a delay, just so we're not peppered way too fast with readings. Really straightforward software. And now I'm going to actually run it. I'm going to split the screen so that we can observe the upload happening and also observe how this photoresistor actually works. I'll go ahead and hit upload. Blinking, blinking, that's a good sign. And the TX light is on because it is transmitting data right now. I want to see that data, but instead of watching it in the serial monitor, which will just show me a list of numbers, I actually prefer to look at the serial plotter because that's a graph. And graphing this stuff over time is certainly preferable. Sorry, my graph showed up in another window. Graphing it over time is preferable. Remember, we got to pay attention to the label on the axis. So this is between like 600 and 606 or something. Now, if I subtly bring my hand over the photoresistor and start getting it closer, notice those numbers are changing just because I'm shielding the thing from ambient light. So that's going up and down. If I cover it all the way, in my case with my finger, it goes down to about 200. And if I uncover it, the ambient light in the room is about whatever 600 means. Now I happen to have a flashlight with me. I'll turn the flashlight on. This is pretty bright. If I shine it right in there, it doesn't get all the way up to 1023, but it gets kind of close. It's like 900 something. Now there's a cool thing about this flashlight, and I was just noticing an interesting pattern. So first of all, if I get it farther away, it's dimmer. Closer is brighter. Sure. Do you see those little spikes? There's some sort of time variance in this flashlight. Though it's just on all the time, there's actually a variation occurring, which the photoresistor is seeing and which we cannot see with our naked eyes. So I'm going to actually make this dimmer by tapping it once. This is a dimmer light. And if I point the dimmer light, look what happened. We actually see a zigzag, and you can actually notice some weird feedback on the camera. The zigzag is indicating that this flashlight is doing what? It's actually PWMing. It's turning on and off really fast. That's how it gets dimmer. Just as we learned about PWM, this flashlight is doing that. I'm going to make it dimmer yet, one step dimmer. This is the much dimmer mode, and now it's like a way faster, weirder looking PWM. So this is kind of cool because we can investigate things that are changing very quickly, invisibly to our eyes changing. But it's not invisible to this. It's not invisible to the Arduino because it's able to update really, really quickly. We're asking it to update every 5 milliseconds. If I go through some other modes, this is the flashing mode. It's actually flashing. Can you read it? Short, 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 long, 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 short, short, short. It's flashing SOS. And this is a faster flashing mode. If I want to know exactly how fast is it flashing, and I apologize for the flashing on the screen, that might be a little bothersome to you, we could actually just look closely at that graph and see what the distance is between those numbers. So actually we could use this thing as sort of a meter for all sorts of different speed tests and stuff like that. So you can use it for proximity, you can use it for testing the brightness in the room, you could maybe know when the door opened, because when the door opens the light shines in, stuff like that. All sorts of possible applications. It's a nice little sensor, it's low cost, and it's pretty easy to use.